Hi, and welcome back to another edition of Easy Theory. So today we're going to be looking at this language we're going to call L to be all the strings of the form zeros in the set 0 star, 1 star, 2 star. So that means zeros followed by ones followed by twos, such that the number of zeros plus the number of ones in W is even and the number of zeros in W is odd. And another way to say this is that the number of ones is also odd because an odd number plus an odd number is an even number. And the other condition is either that first condition or the number of ones is not the same as the number of twos. And this is the one that we should actually be focusing on because the first condition actually is regular. If we just focus on that first condition, it's regular because we can just keep track of whether the number of zeros we've seen is even or odd, and the same thing for the number of ones. So what can we do here? We're going to show that L is not regular. And if you use a standard pumping lemma style argument, yeah, you can show that this language is not regular. But what we're going to do is we're going to use an advanced technique called the P factorial trick. So what is this trick here? What it is we're going to exploit P factorial to arrive at a string that initially had the number of ones being different than the number of twos, and we will pick a value I such that the resulting string has an equal number of ones and twos, and so we will leave the language in that case. Okay, so how do we actually prove this? So what we're going to do is we're going to start very similarly to every other pumping lemma proof you've ever seen. So let's suppose that L was regular. Then from that fact, we know that there exists a pumping length, let's just call it P, and so the P here, of course, is going to correspond to P factorial, P for L, and remember that P is representing the number of states in a hypothetical DFA for L. So now what string are we going to pick? Well, we got to pick a string, of course, that is in L and is of length at least P. So one that you could pick is something that satisfies the first condition and the second condition. What we're going to do is we're going to choose a string, choose W equal to, well, it's not going to have any zeros in it because we're trying to violate this second condition right here, and we will violate the first condition at every point. So essentially what we're really just asking is that this second condition is true. So choose W equal to, well, I'm going to have P ones in the string, and the number of twos that I'm going to pick is P plus P factorial. So if I just picked P twos in this string, well, then it would have the same number of ones and twos, and it would violate this condition. So, and the number of zeros in this string is 0, and so it's not odd in the first place. So we never will satisfy this first condition. So I'm only showing this as a different way of proving that this language is not regular. You can use this condition and use a different string. This is just a totally different method. Okay, so what are we going to do with this string? Well, note that the number of ones is not the same as the number of twos, and so we're satisfying that, which is good. So now what we need to do is to look at all decompositions. So look at all decompositions of W into three parts, X, Y, Z, such that the length of Y is at least 1, according to the pumping lemma, and the length of X, Y together is at most P. Well, if the beginning of the string, the prefix, which is X, Y here, is length at most P, well, then that means X and Y are both in the set of ones. So the only one that really matters for our purposes is the Y. It has at least one occurrence of 1, but we don't know necessarily how many. So we're going to let A to be the length of Y, which we know to be at least 1 for sure. Okay, well then now we got to choose a value I such that if we repeat the Y part I times, it is not in the language. And why do we want to do that? Well, if it was always in the language, no matter what value of I that we picked, that won't give us a contradiction. If we find some value of I that leaves the language, then that will give us a contradiction, because the lemma says if the language is regular, you're always in the language. Well, here, if we want to show a contradiction, then we got to find the value of I that leaves the language. Okay, so what are we going to do? Well, it's not immediately obvious which value of I to pick. So let's just look at it in a general case. So if we just picked a value I, then let's just see what the string actually looks like. Well, we have A characters in Y, and so therefore we have the length of Y being, or at least this Y to the I part being I times A, because there are I occurrences of that thing. And we had one occurrence of Y at the start, so that means we are adding I minus 1 times A number of ones into the string. So that means we have, so originally we had P ones to start with, and then we added in I minus 1 times A number of ones into the string. Because we started out with one occurrence of Y, we got I now, and we are just adding I minus 1 more Y's into the string. And we never hit the run of 2's at the end. So there we still have P plus P factorial. Okay, so what can we do with this? So this is in the language if and only if the value P plus I minus 1 times A is not equal to P plus P factorial. And why is that? Well, we have no zeros in the string, so the number of zeros is not odd, so this condition is not satisfied. So it would have to satisfy this condition, which is what this is saying right here. So what do we do with that? Well, this is equivalent to saying that I minus 1 times A is equal to P factorial, because I can just subtract P from both sides and it's equivalent to this statement here. So what can we do? Well, is there a way that we can choose a value of I so that not equal, that was my mistake. So is there a value of I that I can pick that will have this be equal to P factorial? So it turns out we can. So let's pick I to be equal to 1 plus P factorial over A. So let's actually look at what happens. Well, I minus 1 times A is equal to, we'll just substitute this guy in. So then we have 1 plus P factorial over A minus 1, because of this minus 1 here, times A. The minus 1's cancel, and then the A's cancel, so because it's P factorial over A times A. So this is P factorial. And why does this value work? It's because that no matter what value of A is, the length of the value A, which is the length of Y, is divisible by P factorial. If you divide A into P factorial, it will divide evenly, because P factorial is 1 times 2 times 3 times whatever up to P. And we know that the length of xy is at most P, so that means that the length of y itself is at most P. So that's the reason why we picked P factorial here, is that the length of y divides P factorial directly. Whatever the length is, it will always divide P factorial. So if we look at the final string, well, we get xy to the I, z, is going to be 1 to the power P plus, now just substitute this in, this value of I in, it'll be 1 plus P factorial over A minus 1 times A, and then we still have the run of 2's at the end. But we just figured out that picking this value of I, this term right here will be P factorial. So this is 1 to the power P plus P factorial, 2 to the power P plus P factorial. And look at that. We have arrived at a string that has the same number of 1's and 2's, And since it has no zeros in the string, that means that this condition is violated and the first condition was violated. And so it is impossible then that for this string to be in the language, and so therefore is not in the language. And then therefore L is not regular. So this is actually a really advanced technique, and we were using the divisibility properties of p factorial to arrive at a string that is not in the language here from a string that originally was. So that was called the p factorial trick. It's an advanced technique, but is a very powerful one. So as I mentioned before, you can show that this language is not regular just using a standard pumping lemma technique. This is just a completely different method, but is very, very cool nonetheless. I hope you agree. So I hope that was interesting. Leave a comment below if you were able to show this language was not regular a different way. If you want to support the channel, there are plenty of links in the video description, such as our Discord server, Facebook page, Twitter page, Facebook group we just started, many different ways to support the channel. I would encourage you to like and subscribe to the channel if you find this content useful and you have learned something. And as always, I will see you next time.